right off the bat, we're jumping into something completely mind-bending. I mean, we're talking about an event that unfolds in less than a single second, but somehow manages to release more energy than our entire sun will produce in its entire 10 billion year lifespan. Yep, a supernova. Now, you might just picture a star simply, blowing up. But in this explainer, we're going to zero in on those final, physics-breaking seconds of a star's life. We're talking about matter crushed literally beyond imagination and temperatures spiking to hundreds of billions of degrees. So what actually triggers this whole thing? What exactly goes down in those last few fractions of a second? To really get it, we have to frame the supernova not just as some giant explosion, but as a total, catastrophic failure of physics itself. And, as we'll see, it's a type of destruction that's fundamentally essential for our universe, and honestly, for our very existence, to be the way it is. Section 1. The War Inside a Star. Okay, let's dive right into this. To understand how a star dies, we first have to understand how it lives. See, a star isn't just some peaceful ball of fire floating out in space. It is a relentless billion-year battlefield. On one side, you've got the immense inward pull of gravity, which is constantly, relentlessly trying to crush all of the star's mass down into a tiny, ultra-dense point. But pushing back on the exact opposite side, you have the outward push of nuclear fusion. Deep down in the core, atoms are violently smashing together, releasing enormous amounts of energy that pushes outward. This incredibly delicate, perfect stalemate is what we call hydrostatic equilibrium. As long as the star has fuel to fuse, it successfully holds gravity at bay. But the very second that fuel runs out, gravity wins. Section 2. Countdown to core collapse. Let's look at the life cycle of a massive star, say roughly 20 times the mass of our own sun. In the cosmos, living fast definitely means dying young. Because these massive stars burn so much hotter, they chew through their fuel at an exponentially higher rate. I mean, just look at the breathtaking acceleration on this timeline. A star like this might spend 10 million years comfortably burning hydrogen. But as that runs out, the core contracts, heats up, and frantically ignites heavier elements just to fight off gravity. Helium burns through in maybe a million years. Carbon? That lasts just 1,000 years. By the time it gets down to silicon, the star is in an absolute desperate frenzy. It burns through its entire silicon supply in just one single day. The countdown clock speeds up exponentially until the final core collapse happens in mere milliseconds. And the real kicker? That silicon burning leaves behind a totally deadly byproduct, iron. Iron literally signs the star's death warrant. Why? Because iron is the most tightly bound nucleus in nature. Fusing iron doesn't release energy like the lighter elements. It actually consumes it. It's kind of like trying to heat your house by tossing the stone foundation into the fireplace. It is officially the worst home heating strategy in the universe. Creating iron completely pulls the plug on the outward pressure that kept the star alive for millions of years. Now, what's really interesting here is the Chandrasekhar limit. Notice how this defines the absolute maximum mass a core can hit before gravity completely takes over. As that iron core grows, it's being supported by just one thing, a quantum mechanical effect known as electron degeneracy pressure. Basically, that's just electrons stubbornly refusing to occupy the exact same space. But this defense mechanism has a strict weight limit of about 1.4 solar masses. And amazingly, this hyper-precise limit is named after a brilliant 19-year-old physicist who calculated the whole thing all the way back in 1930. Once the iron core gets too heavy and crosses this quantum limit, the ultimate unstoppable freefall begins. The physics of this collapse are just mind-bending, and it happens in an absolute flash. The inner core implodes at a staggering 70,000 kilometers per second. That is literally 23% of the speed of light. It compresses from roughly the size of the Earth down to the size of a city in a fraction of a second. It squeezes so violently that it hits nuclear density, which triggers a massive repulsive force, causing the core to actually bounce. This bounce sends a massive shockwave outward. But almost immediately, that shockwave stalls out against all the outer materials still falling inward. So what saves the explosion from just fizzling out entirely? A staggering flood of ghostly particles called neutrinos. They get heated to over 100 billion degrees and deposit just enough kinetic energy right behind the stalled shockwave to miraculously revive it, finally blowing the star completely apart. Section 3. The White Dwarf Detonation. Now we're going to pivot to something completely different. We're moving from the death of a massive living star to the violent resurrection of a dead one.
If you compare the two, a core collapse supernova comes from a massive star and leaves behind a super dense remnant, like a neutron star or a black hole. But a Type 1a supernova, entirely different beast. Its progenitor is a white dwarf, which is essentially a cold, dead, Earth-sized stellar corpse made entirely of carbon and oxygen. When a Type 1a detonates, there is zero remnant left behind. None. The entire star is utterly 100% obliterated.
So how exactly does a dead star explode? Well, usually it happens in a binary system. The dense white dwarf essentially steals mass from its neighboring companion star, growing heavier and heavier until it approaches that exact same Chandrasekhar limit we talked about earlier. But here's the catch. Unlike a living star, a white dwarf doesn't have a natural thermostat to regulate its internal heat. When the pressure finally gets high enough to ignite carbon fusion, it triggers a runaway thermonuclear reaction. We're talking about a massive chain reaction with absolutely no off switch. Within seconds, an unstoppable raging flame burns through the entire star, totally consuming it from the inside out.
I want you to focus on this number here, this absolute magnitude of 19.3, because these white dwarfs always explode at roughly the exact same mass limit. Their explosions produce this immense, incredibly consistent brightness every single time. It's so intense that for a few weeks, a single dead star will suddenly outshine its entire host galaxy. We're talking about outshining hundreds of billions of normal stars combined.
Because their peak brightness is so perfectly predictable, astronomers use these Type 1a supernovae as standardizable candles. Basically, they act as a cosmic yardstick. By measuring exactly how bright they appear from here on Earth, we can calculate precisely how far away their host galaxies are, even across billions of light years. And this was a huge deal. In 1998, astronomers used this exact method to shockingly discover that the universe's expansion isn't slowing down like everyone previously expected. It's actually accelerating. Measuring the highly predictable light from these exploding dead stars literally proved the existence of an invisible, repulsive force that we now call dark energy, a real game changer.
Section 4, the cosmic cycle of life. Let's bring the absolutely terrifying scale of these cosmic detonations down to a much more intimate biological level. And this brilliantly illustrates the true legacy of supernovae. See, the Big Bang, it really only gave us hydrogen and helium. Every single heavier element in existence required a star to act as a fusion reactor and a supernova to act as the massive distributor. Carbon and oxygen were slowly forged inside stellar cores. Iron was forged during those violent shockwaves and thermonuclear detonations. And the heaviest elements of all, things like gold and platinum, were created by rapid neutron capture in the extreme chaotic environments of supernovae and neutron star mergers. Take a look at the elemental breakdown of the human body. 65% oxygen, 18% carbon. This ties the immense nucleosynthesis of the universe directly to you. The iron in your blood, the calcium in your bones, they were literally forged in the heart of these explosions. Every single time your heart beats, it pumps iron through your veins that was once sitting inside a white dwarf star that detonated billions of years before our Earth even existed.
We'll wrap up this explainer with this thought. A supernova isn't just a star dying. It is the universe recycling itself, fundamentally making itself capable of chemistry, of biology, and ultimately consciousness. When you step outside and look up at the night sky, realize that those ancient stars had to die so that you could live. The universe destroys in order to create. So how does it change your perspective, knowing that you are quite literally made of stardust, looking back up at the very explosions that gave you life?